Okay, so today we're working in Unit 2, and we are going to be looking at sine, cosine, and tangent functions. And our goal is to determine the sine, cosine, and tangent of an angle using the unit circle. Just basically review or introduce radians to you and have a look through some things like that. So, what is an angle? An angle, if we take this ray that lies along the x-axis here like that, we can see the little ray there. If we rotate it anti-clockwise around a certain amount of distance, that's usually measured in degrees, until it stops, we get the terminal ray. The measure of the angle in standard form, in standard position, is the distance between the standard position and the terminal ray. We call this an angle in standard position because you can give the same angle, so something looking like this with two rays in that direction, you can get the same angle like that. But usually we place the angles in standard position, and then the second ray is referred to as the terminal ray. Because you remember, a ray is a line which starts at a point and then continues infinitely in some direction. If you take two lines from any particular point and drag them in, create rays, you always create two angles. One angle between them, and then the reflex angle. We're always referring to the standard angle on the inside, usually when we're referring to angles. And this is how we measure angles. This is how an angle looks. So the sine and cosine and tangent function, hopefully you've seen several times before. A sine, cosine, and tangent function is the ratio between two of the sides. So let me give you a little quick overview on what that one is. If we take a right-angled triangle like this one here, and let's say, for instance, that this is 60 degrees here. So when we take a right-angled triangle like this one, and this being 60 degrees, the length of this side, the length of this side here, x, the length of this side here, we'll call it the adjacent A, and we'll call this one the hypotenuse. We have a standard ratio between these two. So for instance, if I was to extend the lines a little bit in this direction like this, and I would have to extend the line a little bit in this direction, I create a new right-angled triangle like that. It's still a right-angled triangle. I extend it. Notice how what will happen is this line here has been extended, but this line here has been extended more. The hypotenuse will have to be extended more than the adjacent. But the ratio at which they get extended is always the same because it's defined by this angle here. So what we look at is what is the ratio between the adjacent and the hypotenuse when we define angles like this one. So for instance, if we take the adjacent and we divide it by the hypotenuse, we will find that ratio. And in this particular triangle, it's always going to be a half. Now, if I just zoom in a little bit here, if I do another triangle, and I make the angle much bigger, it's a bit too big, isn't it? If I make the angle much bigger, like this. So now, I've got an angle which is more than 60 degrees. This is greater than 60 degrees. When I extend this one a little, I have to extend this one a lot more in order to create the same triangle. So the ratio has increased. It's going to be more than a half this time. So what we find is that we have a common function that will tell us, given any adjacent and hypotenuse of a particular triangle, if we know what the angle is, we can know what the ratio is, and that's the cosine function. So the cosine of an angle is and all of the trigonometric functions are a relationship between two of the sides of a right-angled triangle. Based on the angle, it will give us the ratio of one of the sides of the triangles to the other one. So for instance, then, what we can do next, so we get this bit here. So the sine is the ratio of the opposite to the hypotenuse. The cosine is the ratio of the adjacent to the hypotenuse. And the tangent is the ratio of the opposite to the adjacent. Now, hopefully you've seen a little bit more than that previously, and you've seen the unit circle. So this is an extension of the unit circle. The unit circle would normally have one unit length here, like this, on the unit circle. When we do this, we can create a right-angled triangle, and all of the right-angled triangles possible can fit into this particular circle, like this. Depending on the size of the angle given, and the rotation, you'll get the adjacent here. Now, what's great about this in an analytical geometry perspective is the adjacent is the x distance here, and the y displacement in this direction is the opposite. In the unit circle, the hypotenuse is always going to be 1. So if we have the formula that the cosine is equal to the adjacent over the hypotenuse, well, when we get adjacent over 1, it's simply the adjacent. So the cosine of the angle is always going to be the adjacent. Likewise, the sine of the angle is always going to be the opposite. So what we end up with here is this particular point P. This point P here is x comma y. And in the unit circle, it's going to be cosine of the angle, sine of the angle. And the coordinates of this point on the unit circle are always going to be thus. Now, if you enlarge the unit circle by a length r, so if we multiply everything by r, we can get a circle of any size. So now we'll get a triangle in this particular point, and the x coordinate is going to be enlarged as well. And this is going to become the coordinates r cos theta, r sine theta, because everything's just been multiplied by r, and it's r times big. This is how we tend to define our unit circle and our sine and cosine functions. Tangent, can we see tangent here in the graph and everything? Well, if you've got this as the change in y, this is the change in y, and this is the change in x, then the tangent of the angle is the change in y over the change in x, which is gradient or slope. So one more thing we're going to see is that the tangent of theta is equal to the slope of the terminal angle. So it's going to be the slope of the terminal ray, All right. So a little bit of revision there. Next up is, in math and science, the standard unit for an angle is a radian. The standard unit for an angle is a radian. Who here has seen radians before in a previous course? Let me see hands in the air. Who's seen radians on a previous course? Who's not seen radians before? Okay, 2 or 3 of you. So radians are going to be tricky for you guys who haven't seen it before. The radians is great. You need to see it many, many times, and then you start to get your head around it. To begin with, you'll find it tricky. So we don't, only in geometry and sort of architecture and everyday speech do we use degrees. Degrees is a great number. It was a unit of measurement that was invented for circles by the Babylonians. They come from Iraq about 2,400 years ago. They came up with it because 360 is a good number. It's very divisible. 260 is divisible by 1, 2, 3, 4, 5, 6, 8, 9, 10, 12, 16, 15, I think 15, and 20. 360 is very divisible. So it's a very useful number. Some people thought they used 360 because there was roughly 365 days in the year. No, they knew exactly that there were 365 point dot dot dot. Their astronomy was amazing. So they weren't confused by this. That's a fallacy.
Why don't they use the number 920?
Sorry?
Why don't they use the number 720? Like, why 360? Like if it's
Smaller than 720?
Yeah, like why? Since it's a multiple, why don't you just use it?
It's smaller than 720 and still pretty good. They also, their counting system was base 60. You know how we count up to base 10 and then move to a new symbol? They counted up to 60 and then you move to a new set of symbols. So they didn't have a counting system that looked like ours. They have something that looks more like hieroglyphics when it comes to sort of writing the numbers. And 60 is often a very good number because most of the things that you could count in their world would be not more than 60. The largest sort of thing that was sort of countable might be like a herd of goats. You go up to about 60, and then you start with a new herd or something. Anyway, so the radian measure is the standard measure. It makes calculus a lot easier. When you come onto calculus next year, if you differentiate in degrees, the formula is horrific. It's not a whole number. If you do it in radians, then it becomes 1. So trigonometry in calculus becomes much easier when you do it in radians. 1 radian is the angle whereby the length of the radius is equal to the arc length of the sector. So if you increase the angle, the arc length will increase. If you decrease the angle, the arc length will increase. And at this sweet spot, the arc length and the radius are the same. That's 1 radian. It's about 57 degrees. What's more important, though, is if you continue it all the way around to here so that we get a straight line across, then that would be 180-degree rotation, which is pi radians. So a whole circle has 2 pi radians in it. Kind of a useful number. Half a circle. What you really want to remember with radians is this. 180 is pi. Remember that. That's the only fact you sort of need to remember. It's also the conversion. If you multiply a number in radians by 180 over pi, you'll convert it to degrees. If you divide a number in degrees by 180 over pi, you'll convert it into radians. This is the ratio for conversion. One of the first things we need to do with radians is learn the exact value table. So this is our first task for today, is to learn the exact value table. I can see a few people who've had me before, they're smiling, they're like, oh my God. So you don't get a formula sheet, and there are certain values that create exact values. In IM3, you should have studied a topic called special right triangles. For those, if you did special right triangles, it's all about this exact value table. We're going to learn to produce it. So I'm going to do this twice. Once I'll show you just how to quickly churn it out. Firstly, I want to show you so that you understand the concepts here. I want you to understand the concepts. So this is our first bit, is what concepts have we got? So if we take a unit circle, like this one, and then we start to draw some angles. So if we have our ray in standard position like this one, and I rotate it all the way up to 90 degrees here, like this. So here in standard position, what are the coordinates of this point there? What are the coordinates of this point there? So this is the point 1, 0. In the unit circle, remember that the point P is always the cosine of theta, sine theta. So if this is 0 degrees, what is the cosine of 0 degrees? 1. So if this is always the cosine, what is the cosine of 0 degrees? 1. If this is the sine, what is the sine of 0 degrees? 0. Next up is this little point up here, 90 degrees. What's the coordinates of this point? This will be 0, 1. What is the cosine of 90 degrees?
0.
What is the sine of 90 degrees? 1. Let's do another one. What's the coordinate of this point here? -1, 0. What's the cosine of 180 degrees? -1. What's the sine of 180 degrees? 0. What about this point here? So what's the coordinates there? 0, -1. So what is the sine of 270 degrees? What is the cosine of 270 degrees?
0.
Excellent. So we got a few numbers here. Those ones are pretty easy to remember. So this one is going to be 0. This one is going to be 1. This one is going to be 1. This one's going to be 0. Okay, next up, let's break these numbers down into radians. So how many radians will 0 degrees be? 0. They both start off at 0. Remember the unit circle here. So at this point here we have pi. At this point here we have pi. This is 180 degrees. These two are important. So 90 degrees is half of that, isn't it? 90 degrees is half of 180. So what's half of pi? Pi by 2. So we start over here. And this is, we divide 180 twice by 90. How many times can we divide 180 by 60? 3. How many times can we divide 180 by 45?
4.
How many times can we divide 180 by 30? No.
6.
Another one to help you is this one. What's half of 60? What's half of pi over 3?
Pi over 6. Said, 180 degrees, it's 180 degrees and pi, yeah. So before you said it's 180 over pi. So
It's not 180 over pi. I just put that as the ratios, the conversion between radians and degrees.
oh,
Here, I didn't make it a quotient. I just related the two together. Okay. So your special right triangles now. Let's take an equilateral triangle, poorly drawn. What is the angle in an equilateral triangle? This is 60 degrees, isn't it? If I cut this in half like that, this angle would be 90. What would the angle at the top be? This would be 30. If it's an equilateral triangle, and this length is x. Let's say this length is 1. This length is 1. How long is this length here along the bottom? This is 1 over 2. What about the altitude of the triangle? What is the altitude of the triangle? How can we find it? Which theorem can we use to find it? It's a right angle triangle, so we can use Pythagoras' theorem to find it. So from Pythagoras, we are going to get 1 squared equals a half squared plus x squared. Rearranging that, we get x is equal to the square root of 1 minus a quarter. Take a minute to follow me through on the algebra. Take a minute to follow the algebra through. Okay, so simplifying that, we should get the square root of 3 over 4, which is root 3 over 2. This length here is root 3 over 2. So what is the sine? If we can then use this special right triangle we've just made. Firstly, we'll take this one. What is the sine of 60 degrees? Sine is opposite over hypotenuse. What is the sine of 60 degrees? Let me write the words down because you're not thinking, you're just saying rubbish. It's opposite over hypotenuse. This is the opposite, this is the adjacent, this is the hypotenuse. What is the sine of 60 degrees? Root 3 over 2. So this one is root 3 over 2. What is the cosine of 60 degrees? What is the cosine of 60 degrees? 1 over 2. Now we can zoom in on the triangle from this perspective. That will mean that the opposite and the adjacent change. So this one now becomes the adjacent, this one becomes the hypotenuse, this one becomes the opposite, and this is still the hypotenuse. What is the sine of 30 degrees? A half? What is the cosine of 30 degrees? Pop these two in. All we need now is one more special right triangle. So with this special right triangle, this length is 1, this length is 1. How long is the hypotenuse? Okay. Which formula or theorem, which is quite famous for a long time now, could we use to find the length of the hypotenuse? And what is that formula? Can anyone here square 1 without using their calculator? Can you add it to another one? And then can you square root that? And what is that? 1.72. So this one is root 2. Now in the triangle that I've drawn, what type of triangle is this one? Right angle? What type of right angle? It's a special one? Two of the sides of the same length, but not all three. Isosceles triangle. Nice one, John. This is an isosceles triangle. So what is the angles in this one? If one of them is 90, the other two have to be 45s. These two have to be 45s. Now, if this is the opposite, this is the adjacent, this is the hypotenuse. What is the sine of the angle? What is the sine of the angle? And then rationalize? Thank you, Zane. All right. For those that didn't catch that, Zane says it's going to be 1 over root 2, which if she rationalizes it is root 2 over 2. You make the denominator rational. Typically on this course, denominator should be rationalized. She does this by the fact that root 2 times root 2 is 2. So what she's doing is she's taking 1 over root 2, multiplying by root 2 over root 2, which is just 1, giving root 2 over 2. All right, let's pop those last ones in. Where are they? So this one is root 2 over 2. This one is root 2 over 2. Now, tangent. What is the formula for tangent? Oh, come back. Okay. One of the best formulas for tangent is this one. Tangent of an angle is the sine of the angle over the cosine of the angle. This is a formula you should memorize or already know. Sine divided by cosine. So if we take a couple of these, let's say we take these two here, we've got 1 over 2, root 3 over 2. Let me just do the math for you on that one once. So we've got 1 over 2 divided by root 3 over 2. This means, so this 1 stays there, this 1 moves up to the top, this 1 moves down to the bottom, and we get 1 times 2 over root 3 times 2. These two cancel, so basically the denominators being the same cancel each other. We get 1 over root 3. So if you take the sine and divide it by the cosine, 0 divided by 1, 1/2 divided by root 3. Notice the denominators are always the same, so they cancel. You get 1 over root 3. Here you get root 2 over root 2. Here you get root 3. Here you divide by 0, which is not defined. This is the exact value table. Now, this is how you sort of work it out from scratch, but you don't need to. You need to be able to produce only this bit. You need to be able to produce this bit here. That's it. The 0s and 1s are pretty easy from the unit circle. Memorize that, 1 over 2. And there's an easy way to memorize it. If you know that the square root of 1 is 1. So you've got root 1, root 2, root 3, all over 2. Root 1, root 2, root 3, all over 2. That's all you need to remember. If you want, you can remember this one as root 0 over 2 and simplify. You can remember this one as root 4 over 2. Because root 4 is 2. 2 over 2. So it's 0, 1, 2, 3, 4 over 2. And then cosine is just sine written backwards. And tangent is sine divided by cosine. So you need to be able to take a table like this one and write it out. Remember that 180 is pi, so this is half of it. 45 is half of that. 60 is a third of 180. 30 is half of that. This starts at 0. This goes the other way. And then you just need to remember a half, root 2 over 2, root 3 over 2. Then write them backwards. Then divide each one, that one by that one, 1 over root 3. This is the exact value table. Undefined. Okay, we are going to pause there now for a few minutes and do in fact, we'll stop the video there.